Hello, my name is Matthew Ferreira, and this is my lab report on circuits. The purpose of this lab is to predict the behavior of circuits containing resistors in series and parallel, using multimeters to measure the actual values of convention currents and potential differences in circuits, and examine the behavior of ohmic resistors and capacitors. Some materials used in this lab were multimeters, batteries, resistors, ammeters, capacitors, and light bulbs to construct and measure the circuits. Here's a preview of the results of this lab. So the potential difference in the 47 ohm resistor is 0.92 volts. The potential difference in the 100 ohm resistor is 1.96 volts. The DC circuit current was 19.1 milliamps, and the RC capacitor charge and discharge for the 10 ohm light bulb was 32 seconds charge and 28 seconds to discharge. And in the 20 ohm light bulb, it took 67 seconds to charge and 58 seconds to discharge. The first fundamental principle used in this lab was Ohm's law, which states how current through a conductor between 2 points is directly proportional to voltage and indirectly proportional to resistance. Kirchhoff's second law, or the loop rule, states how the sum of potential differences around a closed circuit is equal to 0. And Kirchhoff's current law, or node rule, states at any node in a circuit, the total current entering the node is equal to the total current leaving the node. The procedure for the first DC current was to connect two 1.5 volt batteries with a 47 ohm resistor, a 100 ohm resistor, and 2 ammeters. So we had to record the current readings, and as you can see in the diagram, these current readings were at point I1 and I2. Then we had to use a voltmeter to observe the potential difference at each component of the circuit. The system of this circuit was the circuit itself, and the surroundings were everything else, so the earth and all other surroundings. In the DC circuit, it was predicted that the current would be about 20.4 milliamps. However, the observed current ended up being 19.1 milliamps, which there's a slight difference between the two. When the ammeter was replaced with a voltmeter in the open circuit, the circuit's current dropped to 0 amps as expected. The potential difference was expected to be 3 volts, which is the combination of the voltage of the two batteries, but it ended up being 2.9 volts, which also just a very slight difference. And when the circuit with the voltmeter was closed, the potential difference at the 100 ohm resistor was 1.96 volts, 0.92 volts at the 47 ohm resistor, and negative 1.5 volts at the battery. By the loop rule, the sum of all potential differences was 1.71 volts, which this is very different than the predicted value because the predicted value for the overall potential difference in the circuit was 0 volts. The second step in this lab was to construct an RC circuit. To construct the circuit, we needed a battery, capacitor, and 2 light bulbs, one being 10 ohms and the other being 20 ohms, and these were all connected in series. The charging capacitor is observed through the dimming light bulb, while the capacitor discharges also through the light bulb when the battery is removed. And just like in the DC circuit, the system was the circuit itself, while the surroundings was everything else. Here are the results for the RC circuit part of this experiment. As the capacitor charged, the light bulbs dimmed out, which took about 32 seconds for the 10 ohm bulb and 67 seconds for the 20 ohm bulb. This shows how the current decreases from maximum capacity to 0 as the capacitor charges. When this fully charged capacitor was connected to the light bulbs once again turned on. As the capacitor was discharged, the lights dimmed out, this time taking much longer to do so. The 10 ohm bulb took about 28 seconds to discharge, while the 20 ohm bulb took about 58 seconds to discharge. This represents the decrease in both current and potential difference in the capacitor. Throughout this lab, the calculated values tended to differ from the obtained values. This could be due to multiple sources of error, some of which include the accuracy of the multimeter, improper building of the circuits, mistaken calculations such as rounding errors, the timing of the circuits as in calculating how long the light bulbs dimmed through the charge and discharge, and then the additional resistance in batteries and wires. This lab's discussion question states, what if you charged a capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge, and would this prediction happen in real life? If a circuit has no resistance whatsoever, a capacitor would fully charge. However, this doesn't occur in real life because even without an added resistance, batteries and wires do have a non-zero amount of resistance built into them. When we did charge the capacitor without a resistor in the lab, the resistance within the capacitor and ammeter caused the capacitor to fully charge in about 2.5 seconds.